In this lesson, we're going to be looking at the side length properties of quadrilaterals. We're going to focus on determining the properties of quadrilaterals related to side lengths and diagonals, and we're going to determine the angle properties of quadrilaterals. The outcomes we're going to cover are: describe and illustrate properties of quadrilaterals in terms of side lengths, diagonal lengths, and angles of intersection. Identify and explain an application of the properties of polygons in construction, industrial, commercial, domestic, and artistic contexts. And solve a contextual problem that involves the application of the properties of polygons. Now, I've got this split up into a few different types of quadrilaterals because there are a lot of different properties that we have to be conscious of. So the first is our squares. We're all familiar with squares. Squares have all equal sides and all angles are 90 degrees. What you may not be aware of, though, is that if we draw a diagonal, we said before that a diagonal is a line connecting non-adjacent vertices. So, for instance, in the picture we have here, a diagonal would say be a line roughly like that. Okay, so the diagonals of a square are equal. So if I measure the length of that diagonal, and I measure the length of that diagonal, preferably that would be a straight line. If I were to measure the length of that diagonal, I would find that they were equal in length. Also, the diagonals of a square will intersect to form right angles. Again, if they were straight lines, it's hard for me to draw a straight line by hand, but if they were straight lines, they would intersect to form right angles. So all of the angles in the diagonal would be right angles. So this would be a right angle, this would be a right angle, this would be a right angle, and this would be a right angle. So we'd have 4 right angles. The diagonals of a square also will intersect at the midpoint of the diagonals. What that means is, if I were to cut my diagonal, if I draw where the diagonals intersect, this line right here, this line segment, is going to be equal to this line segment. And this line segment, and this line segment. All 4 of them are going to be exactly the same in length. And that's what I'm referring to specifically is from this line here to here. Okay. Finally, the sum of the angles where the diagonals of a square intersect will be 360 degrees. If I add up these 4 angles, they all add up to 360 degrees. We can see that clearly for the square because we have 4 angles that are 90 degrees each. 90 plus 90 is 180. 180 plus 90 is 270. And 270 plus 90 is 360. So it is true that the sum of the angles where the diagonals intersect will be 360 degrees. Okay, in a rectangle, we know, of course, that a rectangle has opposite sides of a rectangle equal. And we also know that in a rectangle, the angles are all 90 degrees, just like in a square. What that means is that the diagonals of a rectangle will be equal. The diagonals of a rectangle will intersect at the midpoint of the diagonals, so they're very similar to the square's properties. And the sum of the angles where the diagonals of a rectangle intersect will be 360 degrees. So those 3 properties are exactly the same as for a square. The only difference is for a rectangle, if you draw in your 2 diagonals, they're not going to be exactly 90 degrees, the angles of intersection. Depending on your rectangle, it could be much more or much less than 90 degrees. Okay, next we have parallelograms. In parallelograms, the opposite sides are equal in length, and the opposite sides are also parallel to each other. It should be obvious when you look at the diagram here that if I drew in the diagonals for the parallelogram, one here and one here, they're not going to be equal in length. The longer of the two diagonals is going to be connecting the two smaller angles. So it's going to be opposite the largest angle. The largest angle in this particular parallelogram is this one right here, and the longest side is opposite that. Next, the diagonals of a parallelogram will intersect at the midpoint of the diagonals. So that means that this side length right here is going to be equal to this length right here, and this length right here is going to be equal to this length right here. And same is true in parallelograms as is true for rectangles and squares. The sum of the angles where the diagonals of a quadrilateral intersect will be 360 degrees. So what we're saying is, if we measure all of these angles here and add them together, we're going to get 360 degrees. Also, this angle right here, which I'm going to call angle X, is equal to this angle right here, which I'll also call X. They're called vertical angles, or vertically opposite angles. So they're always going to be equal. Now if I call this angle here Y, it's going to be equal to this angle here, which is Y. And that is for the exact same reason. They're called vertically opposite angles. So they're going to be equal. What you'll notice is that the number of properties that are the same from one quadrilateral to the next seem to be dropping in number. So we still have that the diagonals intersect at the midpoint of the diagonals, and that the sum of the angles are 360 degrees. But no longer are both of our diagonals equal in length when we have a parallelogram. And they definitely do not intersect at 90-degree angles unless it's a special type of parallelogram. So it's not necessarily a property of a parallelogram. Finally, we're going to look at isosceles trapezoids. An isosceles trapezoid is a trapezoid in that one pair of sides is parallel. So any trapezoid has one pair of parallel sides. And it's isosceles, just like in an isosceles triangle, because the one pair of sides in the trapezoid are going to be equal. And the pair of equal sides in an isosceles trapezoid are the ones that are not parallel. Okay, so the diagonals of an isosceles trapezoid are equal. They're equal in length again. But the diagonals of isosceles trapezoids will not intersect at the midpoint of the diagonals. What you're going to find is that where they intersect creates two pairs of line segments of equal length, but they don't divide each of the diagonals into two equal parts. And finally, the sum of the angles where the diagonals of a quadrilateral intersect are going to be 360 degrees again. That is true for any quadrilateral. In this example, we're going to determine side lengths and diagonals of quadrilaterals. Han is framing a wall. He wants to check that the frame is a rectangle. If it is, he will know the frame is square. In other words, it is a perfect rectangle. How does he know this? Well, the first thing he's going to have to do is get the measurements of the lengths and the widths of this rectangle, or this potential rectangle, I should say. For a rectangle, we know that the opposite lengths should be equal, and the opposite widths should be equal as well, because they are opposite sides to each other. So in a rectangle, opposite sides are always equal. So he took his ruler and he measured his rectangle, or potential rectangle, and he got these side lengths. So he got his lengths are 10 feet each, and his widths are 8 feet each. So that means that so far it fits the first property in that opposite sides in a rectangle are going to be equal in length. But that's not necessarily enough to prove that we have a rectangle, because a parallelogram also has opposite sides that are equal, but they don't necessarily have 90-degree angles in a parallelogram. And we said that the diagonals in a parallelogram are of different lengths. But in a rectangle, the diagonals are going to be equal in length. So that's what we're going to look at next. To check that Han has a rectangle, he can check that the diagonals are equal. In a rectangle, the diagonals should be equal. So he took his ruler and he measured, or his measuring tape, and he measured the diagonals. And he found that each of his diagonals are 12.8 feet. So that means that his lengths and widths, his opposite sides, are equal in length, and his diagonals are equal in length. Well, that is true for all rectangles. So because the diagonals turn out to be equal in length, Han does have a rectangle here. Okay, so I'm going to summarize this. For each individual shape, we're going to look at the properties. For a square, all sides are equal, and all angles are right angles or 90-degree angles. The diagonals of a square are equal, they meet at right angles, and they intersect at the midpoint of each other. A rectangle, on the other hand, has opposite sides equal, and all angles are right angles. So a square is a rectangle, but not all rectangles are squares. The diagonals of a rectangle are equal, and they intersect at the midpoint of each other. So they aren't necessary, or they don't necessarily meet at right angles in a rectangle. If they do meet at right angles, that means the rectangle is a square. For an isosceles trapezoid, it has a pair of parallel sides, and the non-parallel sides are equal. And in an isosceles trapezoid, the diagonals of an isosceles trapezoid are equal. They intersect to make two pairs of line segments of equal length, but they do not meet at the midpoint. A parallelogram has two pairs of parallel sides, and the diagonals of a parallelogram are not equal, and we said that the longer of the two diagonals is going to be opposite the longest angle, or the largest angle. So they are not equal, but they do meet at the midpoint of each diagonal.